to go over more definitions. We have special types of relations. We have reflexive relation, we have symmetric relation, and we also have transitive relations. So let's write down this definition. Then we're going to go over some examples. Types of relations. Reflexive relation. So first of all, let R be a relation on set A. What's the meaning of that? It means that R is subset of Cartesian products between A and itself. So when we say R is a relation on A, it means that R is a subset of Cartesian product between A and A. We say that this relation is reflexive if it follows the following property. R is reflexive if and only if you take any random element. If you take any random element in A, that element is related to itself through R. If and only if for any x in A, x is in relation to itself over R, or x and x belongs to R. We say that R is symmetric. Symmetric. R is symmetric if and only if for any x and y in A. For any x and y in A. If x is in relation with y, then you can conclude that y is also in relation with x. If x is in relation with y, then you can conclude that y is in relation with x. Or if x and y is a member of R, you can conclude y and x is a member of R. And finally, we have transitive. Transitive relation. R is transitive if and only if for any x, y, and z in A, if x is in relation with y and y is in relation with z, then you can conclude that x is in relation with z. Okay. Reflexive, symmetric, transitive. Guys, note that when you're analyzing being symmetric and transitive, you must have this condition. If you see a relation between x and y, you can move on. If you see a relation between x and y, and you can see a relation between y and z, then you can move on to next step. If you don't see any relation between those values, it doesn't mean that the relation is not transitive. Okay? So let's take a look at this example. Ask you to solve this example. Analyze the following. Which one is reflexive, symmetric, transitive? The first one says, first let's define set A. Set A is the collection of 0, 1, 2, and 3. Okay. Well, R relation R is defined as the collection of 0, 0. What else we have? 0, 1. What else we have? 0, 3. What else we have? 1 and 0. What else we have? 1 and 1. Okay. 2 and 2. 3 and 0. 3 and 3. This is your first relation. The second relation is S, which is defined as the collection of 0, 0. These points, 0, 2, well, 0, 3, okay, and 2 and 3. Now check the last relation T, which includes 2 points, 0, 1, also 2 and 3. Okay, so being reflexive, if and only if for any x in A, x is in relation with itself, or the point x and x belongs to the relation. So as you can see here, your set A has 0, 1, 2, 3. As long as you have 0, 0, 1, 1, 2, 2, 3, 3, then you're good with reflexive relation. Okay, I see 0, 0, I see 1, 1, I see 2, 2, I see 3, 3, so it is reflexive. Well, is it transitive? What's the meaning of that? It means that if x is in relation with y, then you can conclude that y is also in relation with x. So what do we have here? I have 0, 1. Do I have 1, 0? Of course. I have 0 and 3. Do I have 3 and 0? Yes. Do I have anything else to check? No. So it is symmetric. Very well. So let us consider transitive. If x is in relation with y and y is in relation with z, I should be able to conclude that x is in relation with z. Okay, let's see. What do we have here? I have 0, 0, 0 and 1. I have 0, 1. 0, 0, 0, 3. I have 0, 3. What else do I have here? I don't have any 0 to be worried about. 0 and 1, 1 and 0, 0 and 0 is here. 0 and 1, 1 and 1, I get 0 and 1, which is just right here. What about 0, 3? 0 and 3, 3 and 0. Okay, do I have 0 and 0? Yes. 0 and 3, 3 and 3, I get 0 and 3, which is just right here. Well, let's take a look at this. 1 and 0. Okay. 1 and 0, I already checked 0 and 0. I have 1 and 0 there. I have 1 and 1 there. Okay, I have 1 and 1. Then I have 2 and 2. Then I have 3 and 0. 3 and 3. Okay. What's missing here? Can we conclude that this is a transitive relation? Why it is transitive, why it's not transitive. So take a look at this. You have 1 and 0. You have 0 and 3. Take a look at this guy. So it says 1 and 0. 1 is connected to 0. 0 is connected to 3. Do you have 1 and 3 in the collection? You don't have 1 and 3 in this collection. 1 and 3 is missing, so it's not transitive. Transitive? No. So one more time. every element is connected to itself in R. 0 and 0, 1 and 1, 2 and 2, 3 and 3. So here we have the reflexive property for this relation. For being symmetric, we need to check to see if X and Y is in this relation, then Y and X is also in this relation. So let's check each of them one by one. 0 is connected to 1, 1 is connected to 0. 0 is connected to 3, 3 is also connected to 0. So this. What else? That's it. So we only have 2 sets of points to check. So it is symmetric. Now, for being transitive, if X is in relation with Y, Y is in relation with Z, you need to be able to connect X to Z. But we can find 2 points. What are those 2 points? One of them is 1 and 0. The other one is 0 and 3. 1 is connected to 0. 0 is connected to 3. But 1 and 3, 1 is not connected to 3 in this relation. That's why it's not transitive. Very well. So let's take a look at this relation. Is it reflexive? So far, I have 0 and 0. I don't have 1, 1. I don't have 2, 2. I don't have 3, 3. Take a look at the definition. It says for any X in A, you need to see X and X in that relation. So it's not reflexive. Is it symmetric? Well, okay, let's start checking. 0 is connected to 2, but I don't have 2 and 0. Not 2 and 0. So it's not symmetric. So take a look at the definition. It says if X is related to Y, then you need to be able to conclude that Y is connected to X. I have X connected to Y, but I don't have Y connected to X. So it's not symmetric. Now, transitive. Is it transitive? Take a look at this. You need to have two points to conclude that you have X and Z related together. As long as you have 2 points, you're good for the conclusion. If you don't have 2 points, you just don't say it's not transitive. So take a look at this. You have 0 and 2, 2 and 3. Okay. 0 is connected to 2. 2 is connected to 3. Do I have 0 connected to 3? Yes, of course. 0 connected to 3. Well, do I have anything else to check? I have 0, 0, 0, 2. I already have 0 and 2. What else? That's it. 0, 0, 0, 3. I also have 0 and 2. So it is transitive. Awesome. So, is this guy reflexive? We don't even have 0, 0 there. So, nope, it's not reflexive. Is this guy symmetric? Well, I have 0, 1, but I don't have 1 and 0. So 0 is connected to 1, but 1 is not connected to 0. So symmetric? Nope. What are reflexive? Okay. 0 is connected to 1. Do I have 1 connected to something else? Guys, note that in the definition, if x is in relation with y, and you need to have your second point. Do you have your second point? 0 is connected to 1. You don't have anything about 1 connected to something else. So we cannot decide about this one. What about 2 and 3? 2 is connected to 3. 3 is connected to, I don't have the second point to move forward and check this relation. So it is transitive. Very well. So give us more examples. Example. Suppose we define a relation this way. We say that, well, let R be defined on Cartesian product between the real line by itself. Remember that this guy is just a plane. So here you're dealing with the plane. So you are taking a collection of points in the plane. But how do we define this relation? We define it this way. For all x and y in R real numbers, x is in relation with y if and only if x is less than y. Question says, hey, is this reflexive? Is this symmetric? And C, is this transitive? Which case is this? Here we go. So, is this reflexive? Remember the definition of being reflexive. Take 1, for example. Can we say that 1 is less than 1? Is it true? Of course not. So, not reflexive. Is this symmetric? Take 1 and 2. 1 is less than 2, but 2 is not less than 1. It's not symmetric. Is it transitive? Well, if 1 is less than 2 and 2 is less than 3, then we can conclude that 1 is less than 3. So the only property that this relation has is being transitive. We're going to define a new relation on Z. So define T on Z. T be a relation on Z. And we define it this way. We say that for all integers, M and N, M is in relation with N if and only if 3 divides the difference between M and N. What's the meaning of that? It means that M minus N is equal to 3K, K is an integer, or M is N plus 3K. That's the meaning of that. Okay, the question says, well, Do you have a reflexive relation? Do you have a symmetric relation? Do you have a transitive relation? And another question for you is, can you generalize this into divisibility by like L? M is in relation with N if and only if an integer like L divides M minus N. Is it transitive? Is it reflexive? Is it symmetric? Which one is that? So another question for you. Can we generalize this relation? No. Is it reflexive? So it means that M must be connected with itself. M is in relation with M. It means that 3 divides M minus M. Does 3 divide 0? Of course. 0 can be written as 3 times 0. So it is reflexive. Is it symmetric? It means that if M is in relation with N, can we conclude that N is in relation with M? Or in another word, if 3 divides M minus N, can we conclude that 3 divides N minus N? Okay, we know the definition of divisibility. We know that there exists an integer like k that M minus N is equal to 3k. Okay, now multiply both sides by negative sign. You get N minus M equals to negative 3k. But negative k can be called like L. So N minus M is equal to 3L. What's the meaning of that? It means that 3 divides N minus M. So it is symmetric. Well, is it transitive? What's the meaning of that? It means that if 3 divides M minus N and 3 divides N minus an integer, let us call it, I don't know, which one you prefer. N minus, let's call it Z, or S is there. So 3 divides M minus N, 3 divides N minus N. Can we conclude that 3 divides M minus S? Can we do that? Well, let us follow the definition. 3 divides M minus N. It means that there is an integer like k sub 1 that M minus N is 3k sub 1. 3 divides N minus S. It means that N minus S is equal to 3k sub 2. Well, now I just say add these. Add them. If you add these, sorry, you can cancel out negative N and N. What's left? You have M minus S, which is equal to 3 times K1 plus K2. This guy can be called L. 3 divides M minus S. So here we have 3 divides M minus S. So it is transitive as well. When a relation is reflexive, symmetric, and transitive, we call it an equivalence relation. So, equivalence relation. It is reflexive, it is symmetric, and it is transitive. So in general, divisibility is an equivalence relation. So the answer is yes.
Execute.